Hi to everyone. Today I'm going to present our paper, Joint Rotational Invariance and Adversarial Training of a Dual Stream Transformer that yields state-of-the-art brain score for Area B4. This work has been done by Arturo, Deza, and me, William Berrios, at the Center for Brains, Minds, and Machines in collaboration with MIT and Artificial. So let's start. The main question that we want to solve, or we want to answer, or give some clues, is, are transformer good models of the Ventral stream? There has been a lot of discussion on this topic. Also, some scientists have mentioned that, for example, this division in patches of an image when doing the processing for vision transformer, and also the mechanism of self-attention might not reflect how the images, how the computer, how the ventral stream works in the brain in the humans. So how are we going to evaluate this if maybe a model is more brain-like? We base our observation in the BrainScore platform that tries to represent a similarity between stimulus when are gone through the deep neural networks and extract their future representations, and also against the recordings on brain areas like B1, B2, B4, and AT. That happens when you put an electrode to non-primate humans and you record the responses. So at the beginning of the, let's say, of the platform, the vision transformer were not so good as we thought. So a vanilla transformer like BITB32 was like 95 out of 200 places. But after the competition ends, we managed to work with a specific type of transformer model, which was cross-VAT. And in combination with adversarial training and rotation invariance, we managed to get the second place position at the competition, the third place overall, and the state-of-the-art in B4 brain score area at the time of the competition. So what's the main question here? How do we get there? First, let's talk about the architecture. So recognizing objects at vastly different scale is fundamental fundamental challenge in computer vision. And there has been a lot of work that helps in this. For example, in object detection, in video recognition, and also in visual and speech recognition. Also, despite the emergence of global texture bias that you might have seen in the paper of Berrios 2019, recent work done by neuroscientists and the machine learning community mentioned that local texture computation might be pivotal for the object recognition task. So for those reasons, we choose this dual branch vision transformer to extract multi-scale future representations and Gremlin-like local texture computations, which is called cross-VAT, that was developed by a team at MIT IBM lab. So, but another important step here is the training strategy. You might have seen this human-machine persulta divergence. For example, here we have an image of a panda that was predicted with a 60% of confidence by a neural network. However, when we add like a specific type of noise, in this case an FGCM noise, for us this image is still the same. However, for the neural network, it's not the same anymore. It predicts this is like a given, a primate with 100% of confidence, almost 100% of confidence, and this is not like the human brain works. So there has been a lot of work regarding this topic, and one of them is regarding adversarial training. So adversarial training consists basically in having first this original image as a frog. We internally, during the training, we perturb the image. And now the neural network sees this as a dog, for example. And inside the neural network, we relabel that. And we say, OK, this is not a dog. This is a frog. So we find the worst case input perturbation and minimize the adversarial loss. This has been shown in work by Medri, DePello, and Harrington and Deza, that adversarial training yields human perceptually aligned distortions when attacked with this kind of distortions like PGD attacks or FGCM attacks. And also, previous to the competition on the platform, leading brain score models use adversarial training. That's why another reason why we use this. Another aspect important for the competition was rotational invariance. We saw this behavior dataset, part of the competition, that has these 3D images, 3D objects rendering 2D images with different poses, eccentricities, and sizes. So we decided to apply simple but essentially hard rotation augmentation, like 90, 180, or 270 degrees, and also this kind of random crop that makes this effect of object eccentricity. So now let's go to the results. With this combination of the cross VAT and the rotation and the adversarial training, we managed, as I mentioned, to get the second place at the brain score competition, and that led us to the best model for B4 area. Also, we want to analyze the contribution of each step in our pipeline, like the rotation, invariance, and the adversarial training. In this case, we show that each step helps a lot in the average brain score, and the combination of those gave us like this big improvement on B4 area. So finally, let's talk about some assessment of cross VAT model, transformer model. So we have, for example, hope you can see it, this human-machine perceptual alignment via adversarial attack on cross VAT. At the beginning, at the first row, we have this cross VAT pre-trained network, and we have images that has been target attacked to be predicted as a goldfish. So the first row, all the neural network is predicting these images as a goldfish. So the curious thing here is like, as the average brain score increases, this distortion seems to fool a human as well. If you can see, for example, the image here on the right on the human, you can see like it resembles what will be like a goldfish. Also, another important experiment that we managed to work is feature inversion. Why? Because an important goal in deep learning is to learn versatile and high-level feature representation of input data. So how this works? We find an stimuli x0 that produces like the same high-level feature representation of an input image that is on green. So we iterate this, and we synthesize the image by minimizing the L2 norm against this, between these two high-level feature representation of each, the input image and the stimuli. Why this is important? Because there is a limitation of standard neural network representations. For example, here we have x1 prime and x2, and we see that even though they look very different, they map to similar representations, as according in the paper on Ekstrom in 2019. So by doing this experiment, we verify, for example, that the cross VAT that is in the middle with adversarial training and rotation is remarkably good at recovering this structure of images starting from random noise. And also you can see that it resembles almost equal the input of the original image with respect to the ResNet 50. That's a good job, but it's not like as good as the cross VAT. So in order to finish this presentation, there is a question. Does this mean that a brain is a transformer, or maybe a transformer is a brain? So current models and approaches try to work on this topic and trying to align machine perception with human perception. In particular, this brain score competition tries to work on these two sides, in distribution image set and out of distribution image set. So we have done a lot of work in this, and the brain score competition is a good starting point because of neurophysiological data and the comparison with neural networks. However, there is still a lot of work to do. So a future idea model will be like, if we want to align machine perception and human perception, we should take into account multiple data sets or different versions, like adversarial image set, out of distribution, but more harder examples, and also in distribution data image set too. So the answer at the end is no, but we have done like the first step towards realizing how a specific pipeline, adversarial training plus rotation invariance, might help to align this machine perception and human perception. So thank you for everything. If you want to check the paper or the code, you can check it here. Thank you.